I have a question, Professor.
Go ahead.
So when you graphed the differential equation,
Right.
On the second half, I was able to recognize that it was a harmonic function,
Right.
but I did not know how you were able to derive the 1/2 cosine x plus sine x part.
Okay.
I knew it was a harmonic, but I didn't know how to get that step.
Right. That's one thing I certainly want to discuss. Any other questions? All right, then let me share my screen and let's look at that equation. So the equation actually before I do that, let me write the equation on paper just so that you see it and so that there's no confusion about what we're solving. So I want to look at dx over dt. I'm going to write it like this: dx over dt plus x equals sine of t. And for now, I'm going to omit the initial condition. You understand that what you want to do is you want to find the general solution, and then, of course, it's easy to apply the initial condition once you have that. Also, one objective today is to understand how the solution of this equation depends on the initial condition. And that's one thing you need to understand in order to understand these equations in general. On this cheerful note, let's go to MATLAB. And I already started writing some code here. Does everybody see MATLAB on their screen? Yeah, you guys see MATLAB? Yeah. All right. By the way, is this font kind of big enough for you to see? Does it look okay? Do you need it to be bigger? No? Okay. So I already started coding this. Well, actually, I started recoding it because I went through the analysis when I was writing the handout. But I decided that it would be beneficial to start almost from scratch. So the first thing I decided to code here is so the first thing I decided to produce is two plots. One plot shows how the initial condition affects the solution. Here's the first plot. It's on my left. I'll make it bigger, and you see how as the initial condition varies from -5 to 5. Well, this happens, right? And it's obvious from this plot that after a little while, no matter where you start on the x-axis, which is this vertical axis, the solution quickly becomes a simple harmonic. And I think it is also obvious that the simple harmonic has frequency 1, just like the red curve, which is the graph of sine. And that's the first graphic from the latest handout, from handout 5, by the way. Do you want to see the code that I used to produce this? It's in the handout, by the way. Are there any questions about how this was produced? All right, then let's move on. I also separately plotted the last plot here. So I used the for loop, obviously, to superimpose a bunch of plots of the solution. And the loop starts with -5, and it goes to 5. So the last plot that the loop produces is the one that corresponds to initial condition x not equals 5. I'm going to close this now. Actually, I'll minimize this now. And here's the last plot. And again, for reference, I plotted sine of t as a red curve. And you see this in the legend. Right, so here you see how initially the curve goes down, and then it kind of becomes, well, the term that is often used here is steady. But steady is a misnomer. Steady suggests that nothing is changing in time, right? What kind of steady means is that there's steady oscillations. So the curve is not doing this anymore. And as you know, you can think about this differential equation in two different physical contexts. So one context is circuits. It could be an RC circuit driven by harmonic voltage. So this is literally an RC circuit plugged into an outlet. You know that the wall outlet supplies what's called alternating current, which is a euphemism for a simple harmonic. You guys know, by the way, the frequency of the voltage and the voltage that US outlets supply. Manhard, do you know what voltage US outlets supply?
No, I only thing I kind of remember was like back in like high school, like AC and DC direct.
Right.
That's the only thing I can remember.
All right. Anyone else? Any electrical engineers there? Caleb, do you know which voltage the outlet supplies? Wow, you plug, but you use it all the time, right? You plug in your devices, and you trust you trust that it's all right. Well, in the U.S., the standard voltage is 110 volts. It can vary a little bit. It can be up to 120, depending on the situation. And what about the frequency? Anyone? Brenna, do you know the frequency of the alternating current in the US? No.
I do not know.
It is 50 hertz. So 50 cycles per second. Yeah, notice I say in the US. Do you think it might be different than other countries? Did you guys ever travel and did you have to bring like some kind of gizmo to convert voltage and outlets? Yeah. Manhar, where did you travel where the current was different?
I went to India.
Oh,
It's my family.
all right.
Then,
Yeah, cool. What do the outlets look like in India? How are they different from the US ones?
the plug itself is a complete different shape.
Okay, but is it still three-prong?
No, I think it's two prong. There's
So
only
they're not grounded. Terrible.
yeah.
Yeah, Russian outlets are equally dangerous.
Yeah.
Right. And they supply 220 volts, by the way. So be careful if you ever travel there.
Okay.
If you plug in an American appliance into a Soviet outlet without appropriate adapters, it's going to explode, quite literally. Don't ask me how I know. So moving on. Let's think about this. So like I was saying, one way to think about the blue curve is, for example, voltage across the capacitor when it's plugged into like, well, you could say an outlet. Another way to think about this, however, is in terms of temperature. You can also think about this as a light bulb that is cooling in the room, whose temperature is the red curve. So it's oscillating harmonically. This is what the temperature of the light bulb is going to be doing. Notice initially, since its temperature is pretty high, it's going to cool down. And this curve, as you can probably now suspect, just based on our previous experience, this curve is nearly exponential, right? Manhard, does it seem reasonable that in the beginning, the light bulb will be cooling roughly exponentially?
Yeah.
Yeah. So its temperature is much higher than room temperature, right? And it's going to drop pretty quickly. But then when the temperature drops enough, you see this is going to happen. And what you notice is that the temperature of the object, say light bulb or whatever, is going to oscillate with the same frequency as the external temperature, I'm going to say. But the amplitude of the oscillation is going to be different, right? And there's also a lag. The blue curve, the blue harmonic is shifted with respect to the red one. A better analogy here than the light bulb is actually temperature inside a room that is, say, not air conditioned. Manhar, have you ever been into a room that is not air conditioned?
Yeah.
Yeah, yeah. If you travel to India, then the answer is yes, right?
Yeah.
And you noticed how the temperature in the room, well, if you spend there a prolonged time, which nowadays, unfortunately, is the norm, you notice how the temperature oscillates following what's called the diurnal pattern of outside temperature, right?
Yeah.
The temperature outside often behaves like a harmonic. The sun rises in the morning, starts heating things up, right? Then at some point in Stockton in late afternoon, sometime around 5 or 6. In other places, with other latitudes, things are different. But say here in Stockton around 5 or 6, the temperature really peaks, right? It's super hot, and then the sun goes down and things slowly cool down, right? It's not an exact harmonic usually, but it's pretty close actually. So it's pretty safe to assume that if you log the temperature during the day outside in any location, you'll get more or less a harmonic, um, and the amplitude of that harmonic and its phase will depend on the latitude. The frequency does not depend on the latitude, right? Because for I think I'm going to say obvious reasons, but the amplitude certainly will. In California, the amplitude is extremely large because here, well, at least in the olden days, it wouldn't be atypical to have a very hot afternoon sun and a very cool night, right? You can go from say 105 or 110 down to 60, right? So huge oscillations. And then there are other places closer to the equator in the tropics where there is almost no variation in temperature, right? The temperature during the day is like 78, and during night it's like 72, right? Terrible. All right. So think therefore of the blue curve as temperature inside the room, and the red curve is temperature outside. And you notice how the temperature inside is has a smaller amplitude, right? Which makes sense, right? Which makes sense because the room insulates you from the environment, right? And kind of stops the heat, but not completely. And you also see how temperature inside is shifted compared to temperature outside. So it's hottest inside the room, not when it's hottest outside, but a little bit later, right? So if the temperature outside peaks at say 5 p.m., then inside it might peak around 6 or something like that. And I want to return to this example because I think it's actually pretty interesting from the point of view of engineering. Imagine that you have a building with multiple rooms and you want to install an AC system as one would, right? How should you air condition so that the temperature indoors is as comfortable as possible? If you think about it, it's not an easy question, actually. And I think since a lot of you are engineers and some of you are civils, that might be an interesting exercise for you to consider, because that is the sort of thing that, for example, civils face when they design buildings, right? Especially in this state. The classroom building on campus, by the way, is terribly designed, and we'll talk about that. It was designed by chumps who don't know differential equations, and then I will explain why. In the meantime, let's try to do some analysis. So I say, just visually, the blue curve has got to be a simple harmonic plus something that is rapidly decreasing. And that something that is rapidly decreasing, I say, is probably a decaying exponential. And now I'm going to convince you that it's true. So before we get back to code, I noticed from the graph that when I find the harmonic part of the solution, I should work with data that corresponds to relatively large values of time, because the entire curve is not harmonic. So here you see large deviation from harmonicity, right? But after about time 10, it's certainly a safe bet to say that this is a harmonic, right? So when I fit the harmonic, I'm going to select points on the curve that corresponds to values t greater than 10. And let me show you how to do that. I think one person posted a question about that because I'm using a variable called ind. You don't have to introduce it, by the way, but I find it useful. So this is how I select data that corresponds to time greater than 10. I make this variable, then I create new variables which corresponds to the portion of the data that I want to work with. And I call them kind of lazily double T and double X because I still want to sort of connote that I'm working with time and the solution X, but T and X are already taken right above. So I need new variables. So that's my trick for introducing new variables. And first, let's plot double T and double X as blue dots, and let's see what we get. So I'll run this again, and you see the data that I'm selecting here, right? Are there any questions about this? I forget who asked that question. Was it somebody in this group or in the other group?
My question was about the sine function. I don't know.
Right. Okay. So it was probably somebody in the other group. But here, do you guys see what I'm doing? So if you go to the command window, you can type who, and it will show you all the variables that exist in this variable space that were created by the code. And what ODE45 computes is T and X, right? And the size of T, for example, is 101 by 1. So ODE45 decided to compute 101 point between 0 and 20 to form the solution. If you type T and hit enter, here's all the values of time that ODE45 decided it needed to use to compute the solution. And if you type index equals T greater than 10, then you have a vector of logical zeros and ones, and the zeros corresponds to this condition not being satisfied, right? So these are the values of T that are less than 10, and here's the first value of T that is greater than 10. If you type T of index, then this is your double T. You see how the first value is a little bit greater than 10? Right, so that's the idea. And if you type X of index, you select the corresponding values of X. So I'm not doing anything dramatic here, right? Now, what I think some of you still find difficult is how to fit a simple harmonic, right? Manahar, is this your question?
Yes.
Yeah. So my first question is, can I use polyfit?
Like I was thinking about that too, but my problem was that I don't know how to turn into like a line similar to how we did with an exponential function.
Sure, we're not there yet, so we're not thinking about the exponential function yet. We'll get there in a moment. But right now, it's clear that if you look at the plot, that there is a unique harmonic that passes through the blue dots, which I would like to find, right? I need to find its coefficients. There are two coefficients, A and B, say. So it's some A cosine t plus B sine t. And I forget who posted that, but somebody said, well, I try to use polyfit to find the harmonic, and that worked out fine. But then I then I got strange results for the exponential because they were complex, and I don't know what's going on. So for that reason, I would like to ask you guys again, do you think we can use polyfit to find the simple harmonic? Michael, you're shaking your head. Why not?
You can't. It's not a polynomial. It's not a
Exactly.
numeric polynomial.
Exactly. Thank you. So let's agree that no matter how desperate you are, you cannot use polyfit to fit anything to the data other than a polynomial of a certain degree. Does this make sense? So if you forgot, let's talk about how to fit a harmonic. I'm gonna switch to camera mode, the document camera. Let's see. So I guess I gotta stop sharing. All right. And let's go to. Oh, I'm already on this document camera. Very good. So I say that if I take the last several points on the curve, which I'm symbolically going to denote T1, T2, T3, all the way down to T sub n. And let's call the corresponding values of x, x1, x2, x3, and so forth. I say that x should be a cosine t plus b sine t. Let me use a different pen. I think it's going to be a little bit brighter. I use this black pen. So what you want to do to find a and b is form a system of linear equations. And then, of course, you want to write it in what form? So that we can solve it in MATLAB. Jeff, how do we write linear equations in this class? In what form? Jeff, I think you're still muted. All right, Marika, can you?
Sorry, you're cutting out.
Oh, am I cutting out?
For me, I'm lagging a lot.
Okay, that's okay. Am I cutting out for everybody?
No, I think it's just me.
Okay. Okay, fair enough. Emily T. How would you write the system of linear equations in order to solve it in MATLAB? In what form? Did you forget?
I kind of forgot.
Okay. Let's write down that system of equations, and maybe that will jolt your memory.
Okay.
So the first equation is substitute t1 for t. I get a cosine t1 plus b sine t1. The corresponding value of x should be x1. Do you agree?
Yes.
Okay. Keep forming equations. A cosine t2 plus b sine t2 equals x2. And so it goes all the way to a cosine t sub n plus b sine t sub n equals x sub n, right? Now in MATLAB, there's a symbolic toolbox that sadly you have access to. And in principle, you could type a bunch of equations into that symbolic toolbox and use some solve type of command. That is not what you should do. Instead, what command shall we use to solve this linear system? Yes, Brenna.
So use like matrices,
Right, so we should write this system of equations in what format and what form? Which will involve what?
the backslash.
No, now you're talking about the command, right? You just said that we need to use which fun linear algebra objects to write this system?
Matrices?
Matrices, right?
Yeah.
Actually, how many matrices do we need here?
2.
Actually, I'm going to say 1, right? Because the other quote-unquote matrix really should be thought of as what? If it has only one column.
Oh, vector.
Yeah. So the answer I was looking for is matrix vector form. Emily, does this ring any bells? Matrix vector form?
Yes.
Yeah. Do you remember what the vectors are? So there are 2 vectors and there's one matrix. Let's start with the vectors. In fact, it might be easier for you to start with the vector of unknowns, the vector you'll be solving for. What are we solving for? Let's ask somebody else. Let's ask Jennifer. Jennifer, what are we solving for?
We're looking for coefficients A and B.
Right, and we arrange them into what? That starts with the letter V.
Vectors. Wait, V?
Yeah, V. You said it correctly.
Oh, vectors.
Well, into how many vectors do we arrange A and B? How many vectors do you need to find?
I think 1.
Right,
Wait.
so why use plural?
Wait, what?
So why use plural? Because you said vectors, right?
Yeah, because I wasn't sure.
Okay, let's try this again. So we need to find two numbers, A and B, right? And instead of finding, looking for those two numbers separately, we're gonna find them collectively by computing one single what?
Vector.
Right, which we'll write as a column, right?
Okay.
And into which placeholder is A, B gonna go? This, or this?
The second one?
And by the second one, I mean this one?
No.
This one?
The smaller one?
The middle one, right?
The middle one?
Yeah.
Yeah.
Okay. So here, this one is the column vector of unknowns. Okay. So this is one vector that is involved. What is another vector that is involved here? Do you remember?
In the equations we have t and x, so I'm guessing with regards to your code it would be double t and double x.
Well, never mind the code. Let's just look at this system, and let's write it in matrix vector form, and then we'll look at the code.
Okay.
Okay. So the unknown is this vector AB, right? There's one other vector here, and then there's the matrix of the system. So let's start with that other vector. What is the other vector that is involved here? You want me to ask somebody else?
Yes, please.
Okay. All right. Keldon, what do you think?
Can you repeat the question?
So we're trying to write this system in matrix vector form so that we could solve it in MATLAB and find the simple harmonic. Do you understand what we're trying to accomplish?
Yes.
Okay, cool. So matrix vector form means that there are two vectors in one matrix that we need to arrange here. And I wrote down the placeholders, and Jennifer just told us that one of the vectors that is involved is the vector of unknowns, AB, which is right in the middle. I'm asking, what is the other vector? And then my next question will be, what is the matrix? Can you tell us what the other vector is? Where does it go? Here or here?
The one being multiplied by the vector of unknowns.
So here?
Yeah.
And what is this vector?
I'm pretty sure it's a 3×2 vector.
A 3×2.
I think so.
Oh, excuse me. Well, I'm kind of tempted to ask you now how you think of vectors. Keldon, what are vectors? How do you think of them?
Vectors are not only something with magnitude and direction, but
Correct.
they can be added and scaled.
Actually, vectors are things that are added and scaled, right? They may have magnitude and directions, but that comes separately. Now, can you do anything else with vectors? Can you multiply them by default?
From my previous knowledge, you can, but I remember in one of the handouts, it was mentioned that vectors cannot be objectively multiplied, I think.
Well, let me refine that.
Mhm.
We're talking about the definition of vectors, right? What vectors are. And what vectors are, I thought we agreed, they're things that can be added and scaled, right?
Right.
That's what vectors are by default. Now, it does not mean that you cannot do other operations on vectors. And you remember from Calc 3, the dot product and the cross product. But that is not part of the definition. That is something that you add on later, right?
Right.
And actually, if you have vectors that in addition to being just plain vectors, if those vectors can be, for example, dotted or crossed, then what you really have are technically kind of new objects, which you could call perhaps enhanced vectors or vectors plus. It's kind of like, let's imagine you buy a car, right? And if you buy the cheapest Kia Sedona or something like that option, it's not going to have a very good sound system, right? But then you can add on to it if you have the money. So it's the same kind of situation. Now back to figuring out what the other vector should go. Can we multiply vectors? Can I multiply this vector that has length 2 by a vector that you said has size 3 by 2?
Yes.
Is that I can multiply a vector of length 2 by a vector of a completely different size?
Yes.
How does this multiplication work?
Well, I know that two matrix vectors can be multiplied if the number of columns in the first vector is equal to the number of rows in the second vector, and the order doesn't matter here. So
I think I see what's going on. I think you may be conflating matrices and vectors. Do you think of matrices as vectors with lots of columns, by any chance?
yes, I tend to associate matrices.
I think that's what's going on. But didn't we agree that matrices are different objects from vectors?
I think we agreed that the matrix was a type of vector.
Well, let me restate that. Matrices can be added and scaled, right? Just like vectors.
Mm-hmm.
So
Yes.
they are vectors. Matrices are vectors.
Mm-hmm.
But the converse is not true. Matrices can be multiplied row by column. That's what you were describing just a second ago.
Yes.
Vectors cannot be multiplied, agreed?
Yeah. Mm-hmm.
And the dot product and the cross product that you saw in Calc 3, I mean, that's a whole different thing.
Okay.
For example, the dot of two vectors is not a vector, right?
Right.
It's a number.
Yes.
The cross product only exists in what dimension?
The 3 dimensions.
Right. Does it exist in 2 dimensions?
No.
Right. Why not?
It's always 3. Mm-hmm. Because there's always a length, width, and height associated in the 3-dimensional world.
But length and height are also associated in 2-dimensional world, right?
Right, but in the 2-dimensional world, I believe we're missing that third component.
Well, obviously, that's why it's 2-dimensional, right?
I guess technically that third component would be 0. It's still there, but it's 0. So.
All right. Yeah, I see what you're saying, yeah, and I agree with you. And as much as I want to continue this fascinating discussion, I have to jump out of it because we need to finish this exercise.
Mm-hmm.
But have you ever heard of a book called Flatland?
No.
You might enjoy reading it, and I can give you a reference later if you're curious. But let's get back to this. And let's agree that vectors can only be added and scaled by default. They cannot be multiplied. So this prevents this from being a vector, right? Because you don't multiply a vector by a vector.
Right.
Matrices are vectors because they can be added and scaled, but they're more than vectors because they can also be multiplied row by column, right? So guess what this object is that has two columns in it? Since it multiplies, it must be what?
A matrix.
Right, right. It must be a matrix, right? Right. So actually, the matrix goes here. But I said there's not a vector here that is lurking. Where does this other vector have to be?
On the right side.
On the right side, yes. So let's start with the vector of the right side, and that's the name of it. Right hand side vector. Who said right side? Job, was this you? Yeah, Job, what is that vector on the right side?
I think it was Noe, but the right-hand side vector would be all the x's.
Right, so x1, x2, x3, all the way to x sub m, right? And Keldon, I also want to point out here, before I forget, that the number of components here is actually capital M. So just because I draw 4, for example, does not mean that this has length 4. And notice these ellipses here. Right, so I'm just omitting a bunch of components here. But this potentially could be a very lengthy vector.
Can you move the paper so that we can see the right-hand side vector?
Okay, can you see it now?
A little bit more. A little bit more.
Right.
Okay, yeah. Okay. Yeah, I see it. Thank you.
All right. All right. In the meantime, Noe, do you see what the matrix is going to be?
Me, yeah.
All right, tell us.
I believe it's cosine t, and then down that column would just be like cosine t1, cosine t2, all the way to cosine tn. And then on the next column, it'd be sine t1, sine t2, all the way to sine tn.
Exactly. Thank you. Right. So Keldon, anything that has multiple columns and multiple rows has got to be a matrix. I mean, unless you just ignore matrix multiplication and say, I'm only interested in adding and scaling, in which case you can say that this is a vector. But here, of course, we're using matrix multiplication, which works row by column. And you see how if you do row by column, which means dot product, you get this system of equations, right? Do you see it now?
Yeah, I see that.
So this is the matrix of the system. And to find the solution, AB, we're going to use either a linsolve command or a backslash. And the code actually usually backslash because it's faster to type. So if you call this matrix capital A, and if you call this right-hand side, well, in my code it will be double X, then this vector, which I think in my code I call C, can be computed as A backslash double X. And you can think of the backslash kind of crudely as dividing by the matrix. But actually, it's a dangerous analogy because matrix division is not really defined, as we discuss later. What you have is matrix multiplication. And you might say, well, if I have multiplication, don't I automatically get division? Isn't it just the opposite of multiplication? And the answer is no. Remember that matrices are not numbers, right? So with numbers, you can say if you have multiplication and you also have division. But matrices are not numbers. And it may happen that division just fails. So some matrices, for example, do not have multiplicative inverses. And we'll talk about that, and you'll see why that is. But for now, I just want to explain how we form the linear system. So you see what we need to do, right? We need to select the data, then form this matrix on this right-hand side, use backslash. So let's go to MATLAB and let's do just that.
Professor,
Yeah?
do we not need to use the dot before the backslash?
No, you do not want to use the dot, actually, because the backslash, see, refers to, well, undoing matrix multiplication in a way. Think of the system. Think of the system as A times some unknown, let's call it C, equals something known double X, right? Conceptually, you want to multiply both sides by the inverse of A, right? To cancel out A.
Yeah.
So you can think of backslash as computing that inverse.
Okay.
Okay.
Yeah. Thank you.
All right. Any other questions? All right. Let's go to MATLAB then. Okay. Here's the graph. Do you guys see the code? Yeah. Okay.
Yes.
So what I'm going to do now is I'm going to form the matrix. And the matrix is easy to form in MATLAB because of the array operations that we have. So I can compute the first column as cosine of double t. So double t, remember, are all instances of t that are greater than 10, right? I'm working with the tail of my data with these dots, okay? So this is the first column of the matrix, and double t is already a column, which is really handy. And the second column is sine of double t, so nice and easy. Now we can write c equals a backslash double x. And let's see what we get. So first I'm going to just run this, and I'm not going to put semicolon here. So this will display in the command window the output c. All right, so we see the graphs, and you see how the output is -1/2 and 1/2. Right, so those of you who are wondering, how did I get -1/2 and 1/2? This is how. And the first component corresponds to the coefficient in front of cosine, because the first column in the matrix A is cosines, right? So this is the coefficient in front of cosine, and the second 1/2 is the coefficient in front of sine. So let's confirm that. I'm going to add to my last plot now the following. So I'll comment this out so that I don't let's not comment this out on second thought. So what I'm going to do is I'm going to make a new variable. I'll call it double y for consistency. I'm going to compute it as C1. That's the first value in C, which is -1/2, times cosine of double t plus C2 times sine of double t. And let's plot this as circles. So double t, double y, blue circles. And I think I have just erased the previous plot, which was of double t and double x. So let's keep those dots as well for clarity. So let's run this. And you see how the circles are centered right on the dots. Yeah. So this tells me that this is definitely a simple harmonic, and it is -1/2 cosine t plus 1/2 sine t. There's no question about it. All right. Does this answer any questions so far? Okay.
I have a question, Professor.
Go ahead.
Can you go back to the paper and show me what the double T and the double X were?
To the paper or the code?
The paper. I think you had wrote them on the paper. The double T and the double X.
Okay. Let's go back to to this. So here, double x refers to the right-hand side of the system.
Oh, okay.
So these are the values of the harmonic that we're fitting to. And C abbreviates this vector.
So would double T be the
Double T actually refers here to this vector. So this is double T.
and then what was double Y?
Double Y was just a new variable I computed, and double Y was literally A cosine double T plus B sine double T. I don't know if you can see this very well.
Okay.
So I find these coefficients, right? And then I want to check how good the fit is. So I simply compute the harmonic using the coefficients that I find used from the backslash, and I superimpose them on the plot. And they're almost exact, as you can see. Did this answer any questions?
Yes, that answers my question. Thank you.
Lovely. Any other questions before we move on? All right, so let's go back to MATLAB then. And let's continue on. So what I'm going to do is I'm actually going to compute, instead of double Y, I'm going to compute single Y. So I'm going to compute the harmonic that we fitted for all values of T that we have. And replot this. And then this happens, right? And you see how we definitely have the exact fit. And you also see how the harmonic deviates from x in the beginning, right? Okay. So I say my solution x is something that is rapidly decreasing, probably a decaying exponential, plus y that I just found, plus this y. Does this make sense? And my next step is going to be to simply plot the difference between x and y and see what I get. So I should see something that is rapidly decreasing, and then I'm going to do probably exponential fit. So I'm going to close all the windows so they're not in the way. I'm also going to clear everything. So this clears all the variables in the memory so that they don't interfere with the computation. And now we no longer need to look at these plots, do we? But I'll keep them nevertheless. What I'm going to do is I'm going to make a new plot, so yet another figure, and I'm going to plot the difference between x and y. Simply enough. Let's plot this as a blue curve. And run. And there's the difference between x and y. This is what I need to add to the simple harmonic minus 1/2 cosine t plus 1/2 sine t to get x. Right, so once we find this, we're done. Does this make sense? And what is your suspicion? What could this be? Does this look like a decaying exponential? Yeah. Justin, do you remember how to confirm that a plot like this is indeed a decaying exponential? And what coordinates do we need to plot it? Actually, you have Wi-Fi problems, right? If you have Wi-Fi problems, let me ask somebody else. Mark, can you hear me okay?
Yeah.
Okay, Mark, do you remember how to confirm that this kind of plot belongs to a decaying exponential? So what should I plot to confirm that this is a decaying exponential?
I do not fully remember.
Fair enough. Does anybody remember? What can we visually recognize immediately?
We can use that semi-logarithmic. I forgot what the full word is, but you can
It is that word, semi-logarithmic coordinates.
Coordinates, yeah.
So what does it mean? So instead of plotting the function itself, what should I plot?
Just plot the portion from t equals 0 to t equals 4, perhaps, or t equals 6.
Well, if I do that, I will just see this portion. I will still not know that this is a decaying exponential. What does my logarithmic have to do with?
Because if you take the logarithm of the if a supposedly decaying exponential function, you're going to get a line.
Right. So that's what we need to do. So instead of plotting x minus y, we should really plot the logarithm of x minus y, right? If we suspect that x minus y is an exponential, let's plot the log of this, and let's see if we see a straight line. So we agree that if I see a straight line now on the screen, that means that certainly x minus y is a decaying exponential. And then I just need to fit two parameters in that exponential. Since we're going to see a line, we'll just use polyfit, right, with degree 1. And when we plot the log of x minus y, this happens, which might surprise some of you. So Manahar, what do you see here? I think you read the handout, right? So you probably know the answer.
I believe in the handout it said that there was an error. There's an error in the function, the ODE 45 function.
Right. Well, first of all, let's agree that the beginning of this plot is conspicuously a straight line, right?
Yes. Yes.
In the beginning, up to about t equals 8 or so, right? You see a straight line. So if we just look at this, the conclusion is certainly that our data is a decaying exponential, since the line has negative slope as a decaying exponential. But then a lot of people will look at this portion and say, now, wait a minute. I don't see a line here, right? What happened to my line? Why is it not just going down? And this would probably throw most of you at this point, because you're not used to data analysis just yet. Vicky, did you have a chance to read the handout?
No, I didn't.
Excellent. So you don't know why this is happening, right? What would be your guess? Why do you think this is happening, and what should we do about it? Any ideas?
There might be another factor.
There is a factor, you're saying. What kind of factor? A fear factor?
I think maybe there's like another variable playing into this that we haven't looked at.
I see. So your suspicion is that actually, in addition to a decaying exponential, we may need to add something else to the harmonic to get x, right? So the solution x is not just a harmonic plus a decaying exponential. There's something else lurking there. Is that what you're saying?
Yeah.
Right. Okay, that's a fair guess. Does everybody agree? Job, do you agree with that?
It could just be noise.
It could be, or it could be something else. So what do you think? Is it just noise?
What Vicky said makes sense, though.
All right. Did you have a chance to read the handout? It does explain this.
Only a little bit.
A little bit. Okay, fair enough. So let me tell you what's going on. When you work in MATLAB doing numerical computations, which is what you should be doing, you have to bear in mind that you're working in finite precision. So everything in MATLAB is stored to some finite precision, which is called double precision, by the way. And in MATLAB, there is a number that called machine epsilon. Have you guys ever heard of the machine epsilon? Does anybody know what it is? Right. Are there any computer scientists here? Who's doing computer science or computer engineering? Anybody? Okay. Well, let me show you what machine epsilon is. If you type EPS, you see a small number which is about 2 times 10 to the minus 16th. So this is the smallest number that MATLAB can distinguish from 0. Let me show you a quick experiment. So let's say x is 3, and let's say y equals x plus epsilon. Do you see that y is typeset as 3, even though we had the epsilon? But let's type y greater than x. So y should be greater than x, right? Because we added something positive to it. And do you see how the answer is false? So MATLAB thinks that y actually is exactly the same as x. Let's try setting y to x plus 2 times epsilon. You see how y is not typeset as just 3 now? And y greater than x produces 1. Right, so there is a positive number in MATLAB that can be distinguished from 0, and everything less than that is 0, you see. And for that reason, it's not unusual to get a strange plot. So when you plot, let's do this, for example, as I do in the handout. Let's plot x minus y, but not the entire data, but just the values that are greater than 10, for example. So I already have my index here, double t and double x. Let's make double y as we did before, and let's plot double x minus double y without the logarithm. So notice what I get. Oops, I need to make a new figure. Hold on. I think I need to remove this. Okay, I'm running into some errors. Let me quickly figure it out. Okay, so this should be double t. That's the issue. Right. So notice what the plot of the difference of x and y looks like for large values of t. Here's what's going on. Remember, we computed double y by fitting a simple harmonic, right? And we agree that the solution is that simple harmonic plus something that goes to 0 quite rapidly. But because that's so what we're plotting right now is that something for large values of t greater than 10. But instead of a nice smooth plot, what we see essentially is noise. And the reason why we see noise is because, in this case, is because of OD45. OD45 is just an approximation to the solution, right? It computes a pretty accurate solution, but it does introduce small errors each time it makes a step. So what you see is not the true difference between the solution and this simple harmonic. It is that plus errors that come from OD45. And these errors overwhelm the computation in this case. So there's a technical term called signal-to-noise ratio. So here, the signal that we're trying to detect, which is difference between the solution and the simple harmonic, is literally is drowned in noise. It's much smaller than the noise. And you also notice how some values here, because of the noise, are actually negative, right? And when you take logarithm of a negative number, what happens? Do you guys know? Job, do you know what happens when you take natural log of a negative number? Have you ever done this before?
It doesn't work.
It does not work. So what happens? Do you get an error?
I haven't tried it in MATLAB.
Have you tried it on the calculator?
Oh, I mean, not recently.
Not recently. Did anybody try to compute excuse me, natural log of, say, -1. Did you guys try that? Yeah, Jennifer, what happened in your case? Did your calculator explode?
I did it and it said not a real number, or all calculations must result in a real number.
That is what happens with your calculator?
Yeah.
Right. So notice it's not telling you that you have an error, right? It just says, hey, I'm just a calculator. I don't do complex numbers. Manahar, is that what's going on with your calculator?
Yeah. When I did a MATLAB, it gives me a complex number.
Right. So notice, for example, that log of -1 is this strange number, right? No errors. Also, what does this imaginary part look like? Manahar, what do you think is this funny number here, multiplying I?
Pi. Looks like pi. Round it up.
It is pi. Yeah. Does it surprise you at all?
Yeah. I'm now thinking about it. Yeah.
Well, you did not expect that, right?
Yeah. I don't know how like a relationship with the circle and a logarithm kind of meet up. I guess.
Do we agree that suddenly this is so fascinating that instead of keeping working on that differential equation, we should be discussing this?
That'll be fun. Yeah.
That would be fun.
Yeah.
All right. Well, let's not jump around. I mean, this is definitely something that we'll soon discuss. It's actually very much pertinent to differential equations, believe it or not.
Okay.
But let's stick with our analysis and notice that logarithm can be applied to negative numbers, despite what your calculator may have said before, and you get fascinating results. So MATLAB does not have any issues with applying natural logs to negative numbers. For that reason, I remember, I forget who, but somebody at one point asked me when we were like separating variables and integrating dx over x, somebody said, hey, don't you need to write natural log of absolute value of x? Do you remember being told to write natural log of absolute value of x when you integrate dx over x in Calc 1? Yeah, you remember that? Jasmine, why were you told to use absolute value inside natural log in Calc 1?
Was it because we didn't want like a negative answer?
Well, why didn't you want negative answers? Were you punished severely for forgetting the absolute value?
Yeah.
Yeah, they would like take off a point, right? And you're like, there goes my A triple plus. But why weren't you allowed to omit the absolute value? Did you ever wonder? Are you wondering now?
Yeah.
Yeah, turn on your curiosity. When you notice such things happening, you need to start wondering, and more than that, you need to start obsessing about it and trying to figure out why. And the best outcome is that you experiment in MATLAB, for example. Compute a bunch of natural logs of forbidden numbers and see what happens, and try to make some kind of conclusion. Even if you don't find the answer, working on this prepares you for that answer. It kind of creates space in your mind to receive the answer. If you don't work on some piece of math, if you just wait passively until somebody tells you, well, this is how it works, then you see what happens, right? Then you just say, okay, I guess these are the rules, and it's not an efficient way to learn. In the meantime, let's go back to this situation. And I say what we need to do, folks, is simply truncate our data in this case. So instead of working with the difference of t and x and y for the whole range from 0 to 20, let's work with it on the small interval in the beginning from, say, 0 to 5 or something like this. And let's fit exponential to that. Because, again, to be clear, when time becomes large, the exponential becomes small, right? It vanishes very quickly. And then all you see is just noise that comes from OD45. That's what's going on. And that's why the plot of natural log looks choppy. I'm going to use the same device as before. So here we fitted our harmonic. And now what I'm going to do is I'm going to set my index variable to t less than 5. This should work. And I'm going to compute double y as this. But before this line, I need to recompute double t. So let's make a t of index. All right, so now double y is harmonic plotted for small values of t that are less than 5. Let us also recompute double x as x of index. And now we can plot the data, and it should look like a nice decaying exponential, which of course it does, right? So you see this looks a lot like just a simple decaying exponential. And if I plot this in semi-logarithmic coordinates like this, I should see a nice straight line. And there it is, right? So now I can polyfit to this line, and this will give me the exponential. So let's do the polyfit. I'm going to type p equals polyfit. The data is double t log of double x minus double y. Actually, since I'm using this again and again, let's compute this as a new variable. Whenever you use the same computation more than once, introduce a new variable so you don't have to recompute things, and make it a habit. That's how you become good at programming and efficient. Let's confirm that the plot is really good, that the fit is good. So I'm going to plot the data as blue circles, and I'm going to plot the value of p using polyval as a red line. Let's put hold on here. All right, so this is a pretty much is an exact fit, right? So finally, let's look at our p. P has these values in it. Remember, this number is the slope of the line, and this is what goes into the exponent. So I have an exponential e to the minus t, right? Because this number is conspicuously -1. Agreed? Now there's also a constant that multiplies the exponential. Do you think it's this one? Is this the constant that multiplies the exponential in the front? The answer is no, right? As Michael was pointing out. Michael, what do I need to do with this number to get the constant out front?
You need to exponentiate it.
Exactly. So let's exponentiate p2. And the answer is conspicuously 5.5, right? So I say my solution is, let me write this down on paper just so that it's clear. So according to this analysis, the solution should be 5.5 e to the minus t. This is the part that we're going to call x sub c. And then there is the harmonic -1/2 cosine t plus 1/2. And this is the part that in my handout I label x sub p. And I'm not going to confirm this with the plot, but you can do it on your own. You can now produce yet another plot where you plot the solution and then plot this formula and they'll match up. Let me tell you what I'm going to discuss on Friday. First of all, do you see what I did? Are there any questions about what we did today? Okay, so once again, this is all encoded in the latest handout. So look at the handout again if you forget how things work. And do try to recreate everything that I did today on your own, ideally without looking into the handout and without copying and pasting. So if you can sit down and go through the same kind of analysis, it would be really, really helpful. So what I want to do on Friday is I want to show how to derive this symbolically. In the traditional course, the instructor does not waste precious class time by showing how to analyze data in MATLAB, because traditionally you just sit down and write a whole lot of formulas on paper. I don't believe in that. So I think what we did today is much more important conceptually and practically than what we're going to discuss on Friday. But you still need to know how to produce this formula analytically. So we'll talk about what's called the guess and check method, which is sort of expounded on in the previous two handouts. So we'll do a lot of that on Friday. And also, obviously, on Friday, I'm not going to give out the exam as I announced. So I suggested that we push the exam. I was going to push it by a week to October 2nd, so Friday, October 2nd. I kind of want to give it out on Friday, so you have a weekend to work on this. But it's going to be fall break, and I thought it was going to be cruel to have the exam during the fall break. Would anybody have any objections if we push the exam all the way to October 9th? Would that work for you guys? So is this okay? All right, so in my announcement, I said that if you have any issues with that, do let me know. If you must have the exam, for example, this Friday, if you can only take it this Friday, I'll give you the exam if you want. But I thought that I'm really enjoying some of the postings and the discussions forum. It seems that you are kind of discovering things, inquiring, and I don't want to interrupt that with the assessment, because I know from experience that the moment I give out the exam, then all this inquiry, all this curiosity, all this desire to learn stops, and you go into your default must write answers, must please the professor and get points mode. I want to avoid that. I hope we can avoid it completely, but it's probably not realistic. So at least let's defer it a little bit. Also, it occurred to me that I haven't really given you a whole lot of symbolic techniques yet. You have really just two things, right? Separation of variables and use substitutions, right? That's another thing. So I don't want to ask you 10 questions where I ask you, okay, solve this using separation of variables, solve this using a substitution, solve this using separation of variables. So it will be kind of repetitive, right? So I think that we'll have a much better experience if we have the exam, say, October 9th. It's going to be take home, obviously, since you seem to be genuinely working hard on the homework and trying, and you seem to be predominantly honest people, not checkers. I'm going to trust you, and I'm not going to do this thing where I sit and stare everybody on the grid, and you're like not allowed, like your browser is locked, and you're not allowed to look this way or this way. I'm not going to do this medium security prison thing. So I'll give you a couple of days to work on the exam, and I want you to think of it as sort of just homework that counts a little bit more. So to be continued. I'm out of time. If you have any questions or concerns, stick around. We can chat for another 5 minutes. Otherwise, I'll see you Friday. Do read the handout that I just posted. Let me know what you think. And on Friday, we'll do a bit more inspired calculus. Any questions before we disband? No? All right. Well, again, thank you all for being good sports, and I'll see you Friday.
Thank you, Professor.
Thank you.
Bye-bye. Have a good day.
Okay.